I enjoyed it very much. I'm in the landscape, but at the end also the seminar, and I'm very happy to be back. So thank you very much, Jacques, for the invitation. In order not to disqualify myself in this seminar, I also would like to talk about EROI. EROI in the sense of energy, renewables, O2C, and intermittency. The original title I had prepared was the use of intermittent sources for electricity production in Germany, Sweden, and also Europe. So these are the three regions I would like to cover. And here you can see the usual splitting. The 630 terawatt hours of German production is split up in coal, gas, nuclear, and so on. And this is the situation of Sweden, and this is then Europe. And what we can see is Germany burns coal. Europe uses more gas. Renewables are large in the case of Germany here. Sweden is nearly CO2 free because it combines nuclear and hydro, and then biomass. And nuclear is also fairly important in Europe. And the topics I would like to cover is integration of renewable energies in large scales, at the example of Germany. Sweden, can one replace the nuclear power by wind? And Europe, what is the benefit of cooperation? A rather up-to-date topic. So now let me turn to Germany, and of course everything goes under the headline Energiewende. This is again the situation I have shown you before. Now lignite and hard coal is split up. This is sort of the 100% case. And now this situation should be changed in the sense that we only use renewables. So we have onshore wind, offshore wind, photovoltaic. Hydropower cannot be changed very much in Germany. This is the level which, because I don't know it better, I just leave it constant at the moment. And as these sources are intermittent, they will not always be present when needed. Therefore, we need a backup system. And then, if this is the 100% case, when I have voids for the 100% case, of course, I also then, at other times, I am producing surplus, so I have backup and surplus to consider under these circumstances. It has no scale, but it's in itself on scale. The method, how I calculate now those things in absolute terms, and you will see them in a minute, is I just use time series. I use the time series of 2012 for Germany, of the loads, wind, photovoltaic, and now I use those and just scale them to 100%. So photovoltaic and wind should produce these something like the net energy, electricity around 500 terawatt hours. So this is what I would like to produce. This is my 100% case. Hydro cannot be increased. No nuclear power. I consider no import-export. No biogas, because I have of the opinion that biogas or bioenergy has to be used for transportation eventually. Lorries and maybe aviation. I assume that photovoltaic is 20%. This is what is called the optimal mix. So when you, let me say, mix two time series, a periodic one which is photovoltaic and an erratic one which is wind. And now you can ask, let me say, in this case, under what mixing conditions do I need the lowest level of backup? Then it comes to 20% photovoltaic, not more, in energy. Okay, arbitrary is the assumption in splitting between onshore and offshore wind. I assume that 1/3 is offshore. But this only enters at the end in the question, how much power do I have to install? Otherwise, into nothing, doesn't play a role. So the major results are now when you ask simply questions, how much power has to be installed? Enough to serve Europe in good days. So when the sun is shining and the wind is blowing, and what we need for Germany alone, we could on those days when the load in Europe is low, serve whole Europe. So the onshore wind is 176 gigawatt offshore and photovoltaic. So this has to be installed for Germany to have, in my definition, the 100% case. But because we need a backup system, we don't always have, let me say, these good conditions. how much is the power of the backup system? It has to be 88% of what we have at the moment. So it is not, let me say, that this drops to a very low value. Quite the opposite. We have to operate two parallel systems. So the backup power, which we need in addition to those, is 73 gigawatt. The maximal load in Germany is 83 gigawatt. And the backup energy on the other side is low. It is only 26%. The extent of the surplus energy which is produced and under these circumstances is, formally, it is enough to serve Poland. So it has a strong economic value, of course. Dimension of the storage, if we would like to get rid of the backup and replace it by a CO2-free storage, then for the 100% case, we need 660 times the present capacity which we have realized in Germany as pumped storage. The dynamics of the backup system is totally different in comparison to the dynamics which these systems now have in operation, because now the dynamics goes from zero up to basically the load. So one has very strong gradients. The conditions for demand-side management, the cheap electricity price during the day, not during the night. This is because of the 20% photovoltaic. So this, let me say, what you normally hear, the clever housewife then will switch on or have her washing machine switched on automatically during the night, because one anticipates the price is low there, is wrong. Because of photovoltaic, the price is low during the day, which means, let me say, that demand-side management drives us to utilize, let me say, those periods where the economic activities are already large. Or alternatively, the most obvious thing is to integrate Saturday and Sunday, because wind is blowing, sun is shining, we only don't consume so much. So let us consume so much and give up sort of our weekly organizations. The amount of CO2 reduction under these circumstances of the 100% case, not to the level of France and Sweden, which enjoy the combination of hydro and nuclear. The conditions for 100% supply by renewable energies, because many studies quote this possibility. This is the use of biogas, which I did not consider. In Germany, we have 40 terawatt hours now produced as biogas under circumstances where our biodiversity is already strongly reduced, visibly reduced. But nevertheless, under these circumstances, you need drastic savings. Normally, people don't say savings, but rather efficiency improvement. This is, let me say, more popular. Savings down to 30%, not by 30%, but down to 30%. So in this combination, you can have then 100% supply, ignoring, let me say, the dynamics of the system, because with bioenergy, you cannot regulate wind energy or so. But this is a secondary issue. What could be a reasonable share by intermittent renewable energy sources? Maybe the speaker before might address this from his perspective. In my studies, I think it could be something like 40% in energy. What are the costs for the transition? They are very high. So, for example, in Germany now, we produce 20% by wind and photovoltaic. This is financed by the feed-in tariff system. I will tell you a little bit more shortly. But this situation now costs 300 billion euros. This is the situation. And what are the economic implications? They are substantial, whatever this means, but I will come to this. So how much power has to be installed? This is the development of the power, the installed power in Germany over these years here till 2015 or 2015. This is the fossil power. This is the band here of our load. So these are the 83 gigawatt I showed before. And this is the minimum which we have, let me say, at the weekend or our Christian holidays. And then this is the development of nuclear power, which in Germany goes down in steps. And this is now the increase of wind and photovoltaic power. And now you can see here already that in the German case, the installed power corresponds to the peak of our load. So we have now something like 80 gigawatts, 40 gigawatt photovoltaic, 40 gigawatt wind. So this is tremendous. And it is already more, let me say, than what we now have on fossil power. And this is the sum, the total installed power, which increases. Now this is the situation now where we get something like 20% from wind and photovoltaic. But if you now scale up those two, because the rest, hydro and biomass, you cannot scale. then ultimately must go from here to here. Then you have the 100% case. Then you produce this target, which is 500 terawatt hours, which I quoted. Very short.
Yes, 100% is 100% of the electricity comes from renewables.
Yes.
So why do you need backup? Why is there fossil backup?
Because part of this 100% is surplus.
Okay, so you don't consume 100%.
Yes, exactly.
You export
Exactly.
some.
Or whatever you do with the surplus, we will come to this. Okay, so you need the backup in addition. So this is the 100%. So you need, let me say, for the 100% case, a power, I'm talking about gigawatts here, going from here to here. So despite the fact that we have already invested a lot, of course, we have not reached, let me say, the real final destination. We still have to develop these things quite a bit. And in addition, we need, for the 100% case, still the backup system. And it is interesting because we are switching off the nuclear. We have to ultimately increase the fossil power as long as we don't have any other possibilities. So because we need more power than we have at the present. This is now power, and this is the energy which we are producing. So when we look at the nuclear, it is continuously going down in energy. Wind and photovoltaic are continuously going up, and now we are producing more energy by wind and photovoltaic than by nuclear. The fossil energy contribution is slightly going down, but the total electricity consumption, so this is the total value. My reference value is 500 terawatt because of the net electricity, the consumed electricity, not the produced electricity. So this increases slightly. Now the extent of surplus energy. So Germany exports, and this of course is not the surplus. It is just, let me say, how the system operates in this intermediate phase where renewable energies are continuously added. Under these circumstances, the question is, can the fossil power stations now totally be switched off and regulate 100%? No, they cannot. There is always the issue, let me say, for the operator to go through this calculation. Is it better to nevertheless run the coal-burning power station because it's more costly than to switch it on again and so on? So this all enters. But nevertheless, when you now plot the exports against the photovoltaic energy production over the years, then you have sort of a straight line, which is, as you can see, 60-60, about the same. So the electricity export of Germany strongly increases, and numerically the export agrees with what we produce by photovoltaic power. This is, as I said, for 2 issues, but it is just, let me say, sort of back of the envelope, or something one can easily memorize. If you would like to know how much do we export, you just look up how much we produce. Sorry? This is all Germany. Germany. All Germany. At the moment I'm talking only about Germany. Okay. Storage. The idea of the storage at the end is, of course, to get rid of the backup system. The backup system may be coal or a mix with gas, whatsoever, but it produces CO2, so you would like to substitute it by something new, which we don't know what this is. But nevertheless, we can, let me say, assess a couple of things. So the situation at the moment is here with respect to the backup energy to the loads. And now when you add storage, the backup for always the 100% case can be reduced, of course. This is the idea. And ultimately, when the storage capacity to the load is something like 6.5%, then the backup under these circumstances is 0. And this corresponds to this factor of 660 times the present storage capability. But as this curve is a hyperbolic curve, of course, nobody would do this, because in the initial period we win a lot, but then to improve the storage, increase it even further, is pointless. Therefore, one needs, let me say, a more sophisticated approach utilizing different technologies. But nevertheless, when, for example, we have a day storage, then we can reduce the backup from something like 25% of the integral loads, the 500 terawatt hours, to something like now 18%. When we have a weekly storage, it goes down to something like 12%. But in all cases, you still need a backup. So this storage just doesn't do it. This is the monthly storage. And now when we use the 40 million cars, which we happen to have in Germany, utilize the Tesla battery, what we are doing is something like setting up a weekly storage. But when you, of course, now look into how these batteries should be operated, because, of course, let me say, when you bring your car in the garage at maybe 6 o'clock in the evening, then it's empty. One has to expect this, because you used your car before. Now you charge it. So you can use it somewhere around midnight or so. I don't know whether one needs it there. But then at 8 o'clock in the morning, when you would like to go to your work, then again, you expect a charged battery. So somewhere, let me say, between 2 o'clock and 8 o'clock, or 3 o'clock and 8 o'clock in the morning, you expect that your battery again will be charged. So that is ready. And now in this sort of cycle, look for where you can use the storage. I don't see much possibility. Okay, another thing, the CO2 reduction. This is basically, let me say, sorry. So this is the storage capacity in terawatt hours divided by the overall consumption, which I just called the load here, which is 500 terawatt hours. So the capacity has to be 6.5% from 500 terawatt hours, which is something like 33 terawatt hours. Okay? 6.5% of the seasonal storage. So the seasonal storage, 33 terawatt hours, corresponds to 6.5% of the 100% definition in my case, which is the production of 500 terawatt hours. And 500 terawatt hours is the net electricity consumption. The overall electricity production is 630 or something like this, terawatt hours. Okay, so the next topic would be CO2 reduction. So this is discussed in terms of the specific CO2 production or emission for electricity production. So it is kilogram CO2 to kilowatt hours. And this is the renewable energy fraction. This is now, the black curve represents the German situation when we increase the renewables from 0 to 100%, utilizing now the mix which we have in lignite, coal and gas, disregarding nuclear energy. So Germany is not there because thanks to nuclear energy we are down there, and thanks to renewables, now we move in this direction, we are 2015 here. But if we would replace nuclear energy by our conventional mix, we would follow along this line. When we now would give up nuclear but replace now everything by gas, we would march along this line. When we look in, what happens in Germany at the moment, thanks to the growth of renewable energies, we are walking down along this line. And now, of course, when we go up to the 100% case, we ultimately should end there if the rest of the backup system is gas, or we end up here if the rest of the backup system corresponds to the present mix between coal and gas. Okay. Now when we look into others, and this is sort of this is Denmark, Belgium, and these are the interesting countries, France, Sweden, Switzerland and Norway. Now here we have 100% hydro, and here we have the mixes there. So Germany, with all the efforts to go to renewable energies and gas, will not be able, let me say, to meet the situation of those countries which are in CO2 production, which we have already now, because they can work with hydro or hydro plus nuclear. Another aspect here one can see if one wants. If Germany, let me say, what we want to do, switch off nuclear, then to start, if we had done this right away, we would have marched up here. Now, if we had switched, let me say, instead of coal to fully gas, we would march down here. So we would have ultimately, let me say, reached a level which corresponds to the use of renewable energies up to a fraction of 50% or something like this. So the replacement of coal by gas is tremendous, corresponds to quite a substantial share of renewable energies. So this would have been an alternative. Now the conditions for 100% supply. So 100% supply, now when I have the renewable energy divided again by the 500 terawatt hours, my load here, then I would sit here at 1. And here this is plotted against the level of consumption compared to the present consumption. So the present consumption is here, 1. And when I now would like to see, and this is my parameter here, the use of biomass in the form of biogas to produce electricity. So at present we have 40 terawatt hours in Germany. Then if we use this now to regulate the fluctuations which we have, then we can meet this point 1. The renewable energies indeed fulfill the load when we reduce our consumption down to 30%. When we double this, but then we need a colony to get the biomass, we double it, then let me say we only have to reduce to 60%. And only when we triple it, then we are where we are now. Then if the dynamics of those systems would allow it, then with 120 terawatt hours, we would be able, let me say, to meet our consumption with renewables alone. Then you can say, of course, yes, okay, then let's just produce a little bit more or produce more renewables. And maybe then the situation is better. So when I do this, then, for example, I have a special point here, because under these circumstances now, the surplus corresponds to 50% of the load. So I improve, let me say here a little bit, I have not to be so ambitious in savings here or here, but nevertheless, very quickly, the surplus which I produce increases so much that I can think, let me say, this must be an economic limit or so, where it just does not make sense to go beyond it. Okay, so what could be a reasonable share by intermittent renewables? This shows now the energy which is produced. Here now we have the 500 terawatt, which is my goal. Here is the installed renewable energy power. This is now the produced energy against the power, which I assume is linear. Of course, in reality, it will not be linear, because we will just not have these preferential sites for wind energy. If we would like to go to these values, we have to go deeper into the country where the wind does not blow as much. So in reality, this line will be somewhere non-linear, deviate from it. This is the deviation. This is the variation over the various years, our installed power. So I said we are now at 80 gigawatt, and this is what we produce here. Okay, now this is the backup system. Here we are at the moment. This is what we need. These are the calculated curves. And here is then this situation, the 100% case, where the backup and the surplus just meet, per definition. Okay, and now I can say, where do I think that circumstances become critical? So here this shows, shown on the right ordinate, the grid power increases with this share. And the surplus production increases. So here I have a technical problem, and here I have an economic problem. The economic problem is what to do with the surplus. So let me say around this level, around 40% or something like this, the problems might start. Of course, this is sort of very vague or so, but this is, let me say, what I would deduce. When I look, let me say, in the situation of Denmark, or maybe more critical in the situation of Ireland, I can recognize, let me say, that these problems indeed happen on days when they have something like 40–50% production. Ireland is more critical because Ireland is an island indeed, not hooked up like Denmark to another grid. Okay, so what are the costs of the transition? Not that this is the phase where we are now. So this is the electricity price in Germany against the years. So the household price happily increases. This is driven by the feed-in tariff. This is the subsidy for renewable energies. And this is the wholesale price, the spot market price, which continuously decreases. This is, of course, a very interesting economic consideration. So the feed-in tariff for 2015 is 24 million euros. This is a figure, and I'm very astonished that this figure is not discussed in detail, for example, in Germany. But when you compare it with other figures of relevance, for example, energy research in Germany, which is, as far as it is publicly financed, is something like 800 million euros. So there's a large discrepancy. Our budget for research at all is 15 or 14 billion euros in comparison to the 24 billion euros. So this is very strange. Okay.
Feed-in tariff, it's 1/3 of the global increase?
It is, this is the household price, yes. So you have, of course, something like 50% is price and 50% is tax and feed-in tariff, 50%. And the rest, the other 50% is production, transportation, yeah.
But feed-in tariff, it's 6 cents per kilowatts.
Yeah.
And the global increase is 15 cents per kilowatt-hour.
Yeah.
What is the rest?
I see. What is the rest, you think? Why does, okay. So this is, let me say, you have a continuous increase of other elements. For example, in this price, you have maybe, I don't know, 8 or 10 individual components. You have the production, you have the transportation, you have, let me say, expenses for the communities because they have to take care of the grids. You have expenses for new grids to be built. This is all paid by the consumer. Then you have an eco-tax, which is a general tax. Then you have the Mehrwertsteuer, whatever the English term for this is. Okay. So it is a very complex thing, and this was continuously increased. And the one driving element in the last years is the feed-in tariff system, and this 6.3 cents per kilowatt hour add up to 24 billion. Yeah. All the others, everything is increasing, but this has the steepest rise there. Okay, and because of now we have this overproduction of electricity, the value of electricity is declining quite a bit. Okay, so the spot market prices, these are annual averages here. They fluctuate, of course. So it's no business any longer to produce electricity by gas, for example. It is also no business any longer to operate combined heat and power because the limit is something like here, 5 cents per kilowatt hour. And this is already a situation nowadays in Denmark. Denmark, by law, produces electricity together with heat. And this model is breaking down. And the overproduction and the export we have, this is often with negative prices. So Germany finances the electricity use of our neighbors, which is a nice gesture, but nevertheless, not economic. So when you look at the electricity price now in other circumstances and plotted against the wind and photovoltaic power in watt per capita, then you can, let me say, compare this now with different countries. And here you can see, let me say, the European countries. And Germany and Denmark with the highest parts here have the highest prices. So this is the price, let me say, which you simply have to pay when you would like to make the transition. And here you can see in red now in terms of the time development, the situation of Germany, and in blue, the variation, the price increases in Denmark. So this all shows a very high correlation. And this is very clear if other countries, let me say now, would like to start here and go up there, France here, go up there, what they have to pay. And here's the US price. So this is, of course, our strongest competitor. And this is, meanwhile, quite crucial, I would say, this difference in price. So what are the economic implications? I can, let me say, discuss this in terms of the full load hours, which is the energy produced against the production capacity. This is something which enters ultimately the price structure. So the full load hours of nuclear is high, continuously there. The full load hours of gas is going down. And this route here rules out gas power stations in Germany. So we have in Irsching the most modern gas power station in Europe, and this is not operational any longer since 2011 or so, because it is economically just not justified any longer. So this is the consequence of this. And then, of course, you can see, let me say, because this is now nature, because of the fluctuating parts, the full load hours of wind and the full load hours of photovoltaic are very low. Now we are having more offshore wind, and here the full load hours will reside somewhere up there. Okay, so the operation of gas power stations loses economic basis, not only because of the price, This fate will be shared by other thermal power stations also, one after the other, and finally also for a future storage system. It will be subject to the same economic rules. So the storage system will, of course, whatever it is, hydrogen, power to gas, extremely expensive, but the economic operation will not be valuable. The consequences now still on the economy. When you look at, let me say, two of our major suppliers with electricity, E.ON and RWE. So the price of their stock market shares halved. Since 2010, here was Fukushima. So the price went down by a factor of 2. When you look into the total staff of those, also they had to lay off people. So these are further economic consequences. Coal? Now, so coal is, let me say, typically around here, and it is also gradually declining. I showed it with gas because here the effect is directly observable because gas does not operate any longer. You could also show it, let me say, for example, with the pumped storage. Also the pumped storage, not only in Germany, but also in Austria. This is one market, is getting problems. Because when they operated at the high price level around noontime at the peak demand, now there is photovoltaic. Okay, so lessons from the Energiewende. I think I went through all those things and I don't have to repeat it. The market rules, because this is now a session of the economists, are out of force. The price follows the weather and not the demand. And as a physicist, I have always learned it should do this. Okay, let me come to Sweden and the question, can one replace nuclear by wind? So this is now the electricity production against the time, and this is the buildup of nuclear power, and here is the operation of power. This is hydro, this is coal, which is gradually moved out. This is biomass, I think, and green is wind, which is there a little bit. So in this case, like I have seen it, or we have seen it before in France, nuclear in this case is operated more stable. So, sorry, I have to explain this. This is the power versus the time Monday up to Sunday, and then you have the daily peaks there, and this is the situation in the night, and so on and so on, and this is the situation then on Saturday and Sunday, where one needs less, and this is the same all over Europe. So this is the nuclear part, and this daily variation of the load is taken care of by hydropower, which rules out all the fluctuations. Now, the operation of a hydropower plant is not very simple. It is not straightforward. So they can regulate the load, but can they do more? The situation is that a power station in a river, a runoff power station has, or this whole hydro system has also other things to obey. It has to take care of the water supply, flood prevention, avoidance of low water levels, fishing, recreation, and all these things are basically fixed in laws. So there is no flexibility. And then a hydro system has several power stations along the river. So in Sweden they have basically 2 rivers, and along this river, there are the various power stations. So therefore, these power stations have to operate in a coherent fashion to avoid spills. So let me say, if somebody further up, closer to the source, opens now, produces electricity, then a water wave, goes through all the other power stations. And when it is there, the question is now, should it produce electricity? This depends on whether you need electricity. Otherwise, when you don't need electricity, it's a spillover and an economic loss. So the whole thing has to operate in a very coherent form. And this means that there are limits for the power from hydroelectricity, but also from the the temporal derivative of this power. Both, and though they vary during the season. Because of course, let me say, in late spring, there is a lot of hydropower. Later in fall to winter, there is only little hydropower. So this is, at the end, a complex situation. So when we now have a look how this is now, when I calculate again the 100% case, so here I have the loads for various days there. Then here in blue I have the winds, which is erratic. Here now I have the hydropower in dark blue, and this now, as you can see, has a totally different dynamics. and it has its limitations. So whenever it is limited here, then you need the backup system. And these limitations have come from these limitations I mentioned before, that the whole system has to operate in a coherent fashion. So now, under these circumstances, when you would like to replace nuclear by wind, you need a backup system. When the backup system, again, is whatever it is, coal or something like this, or gas, then it produces CO2. So here is the installed power against now the nuclear energy. This is the situation as it is now. So they have nuclear energy, and they have a constant contribution of hydro, which is 62 terawatt hours. And of course, they don't need a backup system, and they hardly have wind. Now, when they would like to increase the wind, then they can decrease the nuclear power. They need, of course, much larger installed power, because the full load hours are differently, or the capacity factors are differently, and they need a backup system. Is a gas backup system, if this is used, and this is necessary for the dynamics, the specific CO2 emission increases by 50%, which of course is not favorable. Photovoltaic is rather ineffective to replace the backup system in Sweden. So this is not a solution. The storage is not meaningful in Sweden at all for let me say, this sort of internal operation, because now hydro, of course, smoothes out the wind to a certain extent. So you are producing surplus at a much lower level. And therefore, if you don't have surplus, you cannot stick something into a storage. Therefore, the storage is not meaningful. Excessive surplus production leads to the, now when you produce, let me say, more winds than necessary, then very quickly you reach the point where hydro is replaced by wind. So you are replacing, let me say, a controllable renewable energy form by a not controllable one, and of course nobody would do this. Okay, then very quickly, my chairman stopped telling me the time. I still have 5 view graphs to show. This is the meaning of 5? Okay. Oh, you got a good treat. Okay, I get the same treat. The benefits now of an EU-wide renewable energy field. So I have data from Germany, wind and photovoltaic, Denmark, wind, Belgium, wind, France, wind, photovoltaic, UK, wind, Ireland, wind, Spain, wind and photovoltaic, Czech Republic, wind and photovoltaic, and later I got data from Sweden. So I can now, for each of these countries, I can prepare a model in the sense that it is self-sustained and works under this 100% sort of condition by itself. And now I can utilize this national renewable energy field and combine it into a European one. And then I can compare, let me say, the situation of this European-wide renewable energy field with a national one for each of those countries. My reference will be Germany because of a lack of time. So when you now look at the smoothing effect, because of course you would expect, let me say, that things are smooth under these circumstances when you have contribution from Spain and the Czech Republic on the other side and so on. Then then I can calculate, or I can demonstrate where actually is the smoothing effect. So I can produce, let me say, I can first compare the duration curve for the loads between Germany, which is dashed, and Europe, which is solid. And you can see, let me say, that the demand is basically the same, because Europe is one economic unit. So the load, our demand, will not average very much. Then I can do the same thing now for photovoltaic, and I can produce, so that I can compare, 1 terawatt hour nationally in Germany and 1 terawatt hour utilizing now this so constructed European renewable energy field. And then you can see the difference is not very much. Of course, it stops here half the year because the rest is night. But again, there is no averaging effect in photovoltaic. Then I can do the same thing with wind, and here I get the averaging effect, because this is the situation of producing 1 terawatt hour in wind for Germany, and this is when I use the European renewable energy net. And this annual curve is much closer to my demand curve. So this is the benefit which I have. So it is only the averaging of the wind which would help when Europe cooperates, because then I get a supply situation which is closer to the load, which means that surplus and backup are reduced. So when I now look at this, and what is the Germany's benefit, and this can be done now for each of these contributing countries, and I did it for all of them, but what is the Germans' benefit when they replace the national field now by the EU-wide fields? Then the backup energy is reduced by 24%, the maximum backup power by 9%, the surplus power by 15%, the grid power by 7%, the typical grid fluctuation level 35%, but this is a long debate, so we should not go into this. And the maximum storage capacity quite substantially by 28%. So there is a benefit, but not all countries have the same benefit.
It's a benefit for Germany?
Yes, this is what I say here. Germany's benefit. Not each country has the same benefit. Why is this, let me say, what is the wind field? I told you is the important element. What is the structure of the wind field? And I express the structure in terms of a regression coefficient when I compare now the data series I have from the various countries with the one of Germany. So the autocorrelation of Germany is of course 1, so this is to compare with, and then you can see when we go to, where do we go here? To Denmark, to Sweden, Czech Republic, to Belgium, France, England, Ireland, Spain. Then you can see that what you can see every evening when you just look into the weather map, that we have, let me say, a weather condition which sits over Europe and has a time scale which goes over the countries. And only, let me say, the Spanish situation and also the Irish situation is somewhat decorrelated of the German situation. So therefore now I can, let me say, discriminate between, again from the point of view of Germany, from a useful surplus produced by the others, and let me say one I cannot use. So here I have the surplus of each of these countries, which I have studied, and just for your eye, I have normalized this to 100%. And then I look, let me say, of the Spanish surplus compared to the German surplus, whether it is useful. And this is this part which is useful because Spain has surplus when Germany needs power and wants to switch off, then can switch off then the backup. So this is the useful surplus, and now again you see just the opposite. Spain is very useful for us because it is decorrelated, whereas Denmark is not so useful for us because it is correlated. But this also tells us in case of a weather condition producing surplus, when we produce surplus, our neighbors also produce surplus. So the handling of surplus is aggravated.
What sort of surplus it is in terms of decarbonized energy or what sort of surplus?
No, surplus would just be, let me say, the wind and photovoltaic power which I produce in excess. So I have, let me say, at the end something like 300 gigawatt installed power, as I have shown it at the beginning. And of course, under certain conditions, they produce much more than what I need. But I need 300 terawatt in the average to produce 500 terawatt hours. This is sort of my target. Okay, when one would like to ultimately utilize the European possibilities, then of course one needs the corresponding interconnection capacity so that I have a copper plate situation for Europe. And in red I have the actual situation, in blue I have what I would need. And this is again normalized against the generation capacity. These values are higher than the generation capacity because this system operates on surplus. As long as I don't have surplus, I use it myself because I don't have another possibility. Only when I have surplus, I can give it to others via the interconnectors. So the surplus has high power levels and therefore the interconnectors have to cope with this. Of course, nobody will realize this. But this means, let me say, that we will not be able to exchange power so freely in Europe. And it also means that we will have surplus which we cannot use. Okay, so Denmark has a high interconnector capacity. They only have to increase a little bit because they are already embedded into their neighbors. This is their tremendous advantage. So they took care that they are not alone. All the others have to increase it drastically. So when we ultimately put the whole thing together, the demand of Europe is this value. This is the existing hydroelectricity. Now, if we would like to have a 100% case for Europe, this is the onshore, this is the offshore wind, this is the photovoltaic, again, under my 20% law. And this is the backup power, or which we still produce, the energy, the backup energy, which we still need, or the surplus correspondingly, under these circumstances, which we still produce. What to do with this? Of course, it is very difficult because it's very erratic. But nevertheless, just to compare figures, the derived heat which we need in Europe corresponds to this figure. The road transportation is much higher, but when we compare the efficiency, let me say, of an electric car compared to a regular fueled car, then it comes also in this order of magnitude. So in principle, numerically, one can do something, but of course, then you must organize it. How to cope with something which is so highly erratic. And now I'm done. Yes. So the EU-wide consequences are large power has to be installed. The national use typically needs north-south grids. The cross-border exchange requires east-west grids. We have already heard how funny it is when you have to develop new grids and how long it takes. Exchange over large distances is beneficial because of this correlation of the wind field. Large interconnector capacities are needed. Not all countries benefit equally from an EU-wide renewable energy grid, or from a grid which we have. And the economic consequences, under these circumstances, utilities lose their business model, like the German utilities did. And an IEA study says that when we go this way to renewable energy, then the prices will ultimately has a consequence that Europe loses 1/3 of the global market share of energy-intensive exports over the next 2 decades. Yeah, okay, here's my final one. If you okay, maybe we go to the discussion. You start the discussion and I look for the last thing here.